Okay. Hi, everybody. Welcome to the Shaders Workshop. If you're here, you might already know what a shader is, but in case you don't, I'm going to go over what shaders are really quickly. But probably the most practical thing for you is that shaders are really cool. And it's a really easy way to add a lot of polish to your game. You can do some really neat effects with shaders that make your game look like you put a lot of work into it when really your shader was only a couple lines of code and you did some cool tricks. So you can get a lot of bang for your buck using them. But they're also tiny GPU programs. What that means is basically shaders are tiny little bits of code that you run on your graphics card, and they process every single vertex of a model and pixel of a triangle that gets rendered, and it produces some output color for every input that you give it. So most of the time, they'll just take their input, modify it a little bit, and produce output. But you can do lots of other stuff with shaders. You can even do generative stuff with shaders, like taking no input and producing randomly generated output. And you can also do, a lot of like mixing of some procedurally generated stuff and some prepackaged canned stuff. Everything that you see on the screen in a game has been run through at least one shader. Basically, it used to be the case that you had to sort of lean on your graphics card to do all of your compositing and rendering for you. You would just sort of pass it assets and say, please render these with a Phong shader, or please render these unlit with some ambient light. But nowadays, that is pretty much completely gone, and when you pass stuff to your graphics card, you also get to write how it takes those inputs and produces colors for each pixel. So the big takeaway is that we can write basically whatever we want to get exactly the look that we want for our game. So what's so great about them? You can get some really interesting and good-looking effects on the cheap. And just as a couple quick examples, you can use them for randomly generating detail, which is super helpful when you need a lot of detail to make something look good, but you don't want to have to make all that detail yourself. You can just throw a nice looking shader on it that will randomly generate the detail for you, and then you can just keep adding more simple inputs, and you'll keep getting really high detail outputs. You can use it for animating textures, which, unless you run it through a shader, is probably not very easy. Animating textures on the graphics card itself by re-uploading images is really slow, and you probably shouldn't do it at runtime or even close to once per frame. But as long as you have all of the resources that you need for animating there already, you can use shaders to actually do the animation for you. For example, when you animate sprites in Unity, when your sprite changes from one frame to the next, it's not actually changing the texture of the sprite that it's rendering. It's really just changing which texture it's rendering entirely. The textures stay completely static. They stay the same. It just switches which one gets drawn onto the sprite. And that goes through their own custom shader for that. Drawing detail in screen space, you kind of know it when you see it with screen space detail. But basically, it's anything that is from the perspective of the screen instead of the perspective of the world. Anything that stays sort of like in the same place on the screen, even when you move around, that's screen space detail. You can sort of see some of this. I don't think there are any prominent examples in popular games, but you can use it for drawing some extra like warning details on stuff. You can use it for drawing outlines around things. Compositing textures, this is a really big one. So basically all of the different blend modes that you have in Photoshop, those are all things that you can use in shaders to composite textures together. And you can use them for a lot more, which is really, really cool. You can use textures for tons and tons of stuff. So today's workshop is going to be roughly 50% structured. I already have a couple demos, and we're going to ease into doing stuff with shaders and get you a good technical foundation, we're going to make a rainbow shader and do some image compositing, so that should be fun. And then the rest, the latter half, is going to be more unstructured. I have a few ideas of what we want to do, but we're going to wing it and try to do some cool stuff with shaders, because part of working with shaders is picking some actual application for it and writing a shader for it. Because it's just like programming. You wouldn't do a workshop on programming without doing Hello World and then doing some other cool stuff. So start thinking of suggestions now for what you want to do with the unstructured half. And while we're doing the first half, it might give you some better footing to think of some cool ideas. So let's go. All the source for this workshop is available right there. That's our GitHub for the Game Dev Club. And the shaders workshop, all of the code for the structured half is already up there. So without any further ado, let's hop in and take a look at some of the results that we're going to get. So these are 3 different shaders. The left one is just a rainbow shader that is animating some rainbow rings that collapse toward the center. The middle one is actually cooler than it looks, but it has a blend mode that we can use to change between a bunch of different image compositing techniques. You might recognize this one as normal image blend. This one is multiply and then overlay, and I think this one is screen. So there's a bunch of different blend modes that I implemented real quick, and I'll show you the source for those and how you can use them. And then the one on the right is putting both of those together so that we have a boost pad like in Mario Kart or another racing game with some rainbow texture. And then we've got 2 textures that scroll up, a main boost pad texture and a detail stars texture. So we're going to show you how to make those. So that's our final product. Let's go ahead and make a new project so that we can start from scratch. I have a couple CG programs already written to help us out with it. So if you need those, feel free to grab them from our GitHub. I guess I'll pull it up real quickly. If you want those CGs, they're going to be in assets, shaders, and then everything that's CG INC, like blend modes, HSV RGB, and that's it. So that's all you need. So we'll do that real quick with our new project. So we'll open it up in Explorer and download those include files real quick. And I'll walk you through those when we use them. Blend modes, this has our implementation of all the different blend types. And then this HSV RGB is an implementation of HSV to RGB so that we can do rainbows. So now we've got our 2 CG includes in here. And we're going to go ahead and make a shader. Much easier than you might expect. All you have to do is right-click in your shaders folder, and then go create, and then shader. And for the first half, we're going to be doing unlit shaders. These are all different types of shaders that work with Unity. Standard surface shaders are ones that you'll probably be working with more so when you want things to look like they do by default, with some additions and modifications. Unlits are typically ones that you want to generate all by hand, or you don't really care about lighting on, which is why they're unlit. Unlit shaders don't show shadows or ambient occlusion or a lack of light in the surrounding area. Standard surface shaders will use global illumination to give you a realistic look. So we'll go ahead and make an unlit shader, and we'll just call this rainbow. So we have our rainbow shader. We want this to go on something, so I will snap to the Y view, and we'll go ahead and make a plane with create 3D object plane. And a plane is basically just a 10 by 10 textured quad. Move that to the origin, and sort of the relationship between shaders and materials is that you write a shader, and then a material is like a shader with a bunch of properties set on it. So we'll go ahead and make a folder for our materials, and we'll make a new material. You can do that with create material. And we'll just call this rainbow. And you can see up at the top that we have this shader drop down. We're just going to select unlit rainbow, which is our rainbow shader that we made. And to apply it to our plane, we just drag it onto there. It looks the same right now, but once we modify it, we'll be able to see that some stuff has changed. So let's start editing the shader. We're going to open up our our C# project, and Visual Studio will eventually open. Oh, sign in. Oh, yeah. For our rainbow shader, what we're going to want to do is draw some rainbow, and then we're going to want to draw rainbow rings, and then we're going to want to draw rainbow rings that actually move. So our fundamental concepts for this are going to be a lot of math. In case you were not ready, shaders are a lot of math and sometimes not super intuitive math, because shaders are all about transformations. So when we get stuff into our shader, basically all that we get as input is our UVs, and that's it. The UVs are the texture mapping coordinates for our model, and our quad will just have 4 UVs. The UVs are going to be 0, 0 to 1, 1. So this is x0, y0, x1, y0, x1, y1, and x0, y1. And then all of the pixels that we shade in between here with our shader that get drawn to the screen, we'll have interpolated values of those 4 UVs. So right in the middle, we'll have 0.5, 0.5 as our UV. Up here, we'll have somewhere around 0.25, 0.75 as our UV. So we have to somehow take those and then translate it into rainbow. So let's go ahead and open up our rainbow shader in Visual Studio. So this is kind of 2 things put together. Unity shader format is a wrapper around some CG code. CG is NVIDIA's own shading language. The reason why we use CG instead of something like GLSL, if you're familiar, or HLSL for DirectX, is that CG can be compiled to both GLSL and HLSL. So when you compile your game and make a build for WebGL or for Android, for iOS, PC, Mac, Linux, it will take each of your shaders and it will compile it into the right shader for your platform. So we sort of write in this platform agnostic CG language, and that will compile down into each platform specific language. CG is pretty good. It has a lot of features that are very helpful, and it's a pretty strong language overall. So the first part is this shader, and this is going to tell Unity where to put our shader. So ours ends up in unlit/rainbow, which you might remember if in the rainbow right here, it's in unlit rainbow. If we change that, it will put our shader somewhere else. So if you want your shader to end up somewhere custom, you can do like my game/rainbow, but we'll leave it in unlit for now. The first subpart is properties. These are anything and everything that ends up in your inspector when you have your material with your shader on it selected. So this texture right here that shows up in our inspector is this texture right here that we've put in our properties. Next, we have our subshader field, which tells our shader how to render each of our passes. So we have a tag here of opaque. That means that when we go to render this, we'll render it front to back instead of back to front, which you have to do with transparent renders. The reason for this is when you render stuff on your GPU, you render into what's called a depth buffer, which basically says what's the distance away from the virtual eye that each of the pixels are. So when you render something physically, it renders the colors to the screen, but it also renders how far away they are from you into the depth buffer. And when you render front to back, the thing closest to you will put its depth in the depth buffer first, and then anything else that would render behind it would look at the depth buffer first and say, oh, there's something that's closer to the screen than I am, I shouldn't draw there, and it won't draw there. The reason for this is primarily optimization. It reduces what we call overdraw. Overdraw is when you run a shader to create the color for a pixel and then end up not using it anyway. So common sources of overdraw is if you draw in a random order or if you draw back to front, that'll maximize your overdraw because you're guaranteed that if something can run its shader for all of its pixels and then get all of those overwritten, it will. So rendering front to back with your opaque render type guarantees that we'll minimize our overdraw. When you have your render type set to transparent, it does render back to front, which is why transparent things are more expensive to draw. And the reason it draws back to front is because you have to obviously see what's behind your transparent thing, or else it doesn't look transparent. So we'll leave that alone. We won't have to mess with that much, but if you do want to do anything with transparency, you'll have to change that render type. Those are all documented at Unity. And then LOD is your level of detail, 100. That's just like the default. We can leave it alone. And then inside of our pass, we have CG program and NCG, and that tells Unity, I'm going to start writing some CG now. So this is our actual shader. This is our rainbow shader right now. These three pragmas at the top are compiler directives. So we're telling the CG compiler our vertex shader is vert and our fragment shader is frag. Each of these functions will take in, for the vertex shader, it will take in a vertex and it will generate some information to pass to the fragment shader. And the fragment shader will take in whatever the vertex shader generated and output a color for the pixel. So a vertex shader might do things like push some vertices around. For example, if you had a sphere and you wanted to make it like a wobbly or something, you could randomly push around the vertices in the vertex shader, and that would give it that like warped and constantly moving sort of look. The fragment shader will take whatever the vertex shader gives it and produce that color. We're going to go ahead and get rid of this multi-compile fog. We don't really need fog right now, and so we can just discard that. This #include unitycg.cginc is saying we're going to include all of Unity's default functions. We'll leave that as it is for now because we need that. And then we have two structs. We have appdata and v2f. Appdata is our per vertex data, which our per vertex data is going to be vertex, which is going to be the position of the vertex, and UV, which is going to be our first texture coordinate. So pretty standard, what you would think of when you've got a model in Maya. Each vertex has a position and a UV coordinate. And then our v2f struct is going to be the stuff that we pass out of our vertex shader and into our fragment shader. That's why it's v2f. We can go ahead and get rid of fog coords, and we have the same stuff in here. We still have our UV, and we still have our vertex. So then we have sampler2D main text and float4 main text st. These are tied to our main text property. Anything that we put up in properties, we have to also define in our CG program. So even though we've told Unity we have a variable main texture that's a texture 2D, and I want it to say texture, we still need a sampler, which is sort of how shaders interact with textures on the graphics card. We need this sampler to be able to look at specific pixels on our texture. And this main text ST is basically a bunch of properties for the main texture. In here we have this tiling and offset. That's our main text ST. If you're not going to use that, you don't really need to include it. Unity won't complain about it. We won't be using it, so we'll get rid of that. In fact, we won't be using main text either, so we can get rid of those. And we can get rid of main text up there. And then V2F vert, this is our vertex shader. That's it. That's the whole vertex shader. We take in our app data, we make a V2F to pass out of the vertex shader, and then we say our vertex is Unity object to clip pause. That's just taking our world space position and translating it into screen space. And then we set our UV to transform text VUV main text. We don't really need this whole line. We can just do VUV. The transform text will make sure that we apply those transformations from the main text ST that are like the repeat and the offset. But we won't be doing that. We just want our raw texture coordinates to be passed out of our vertex shader and into our fragment shader. And then the Unity transfer fog we can also get rid of because we're not applying fog. So basically what our vertex shader does now is we make a V2F output. We set the vertex to our input vertex. We set the UV to our input UV, and then we return it. So this will get passed from our vertex shader into our fragment shader. So what this does, our fragment shader returns a fixed 4, which is basically saying a fixed point number times 4 for 4 components. This is basically a color, RGBA. And we take a V2F as input, and SV target, I'm not 100% sure what that does, but I usually just leave it there. I'm pretty sure that it has something to do with saying that this is what we're going to return as our color for our pixel from our fragment shader. So right here, what we do is we use our sampler to get a color. We don't need that anymore because we don't have a sampler. And then we apply our fog, which we don't do anymore either. So now it's literally just return a color. So since our color we originally got from our texture is no longer there, we can just return whatever color we want. So I guess our hello world for shader will be to turn our quad red. So we're going to use a float 4. I'm going to change this from fixed 4 to float 4. The difference between fixed and float is fixed point numbers are usually a little bit faster, but less precise. They don't have the range that floating point numbers do. Floating point numbers are more complicated to do arithmetic with, but they have a really big range. They work at small scales like between 0 and 1, as well as large scales of greater than a billion or a trillion. So when you're writing your code, I would suggest using all floats unless you know that you need to use fixed, because when CG compiles your code down, unless you're making a build for Android or iOS, it'll probably use float under the hood anyway. So fixed is kind of unnecessary. You can pretty much just ignore it. So we'll return red from our fragment shader. So red is going to be 1 on our red, 0 on our green, 0 on our blue, and then 1 for our alpha. So if all goes like we sort of expect it to, our quad will be red when we look at it. And there we go. So what's happening here is our vertex shader is interpolating all of our vertex properties for us, and then our fragment shader is taking each of those and saying, this pixel should be red. So let's do something cool with it now. So this HSV RGB.cginc file has a tiny implementation of an HSV to RGB function. So we take in HS and V all of which are between 0 and 1, and then we generate our G and B between 0 and 1. So now that we know that we have a function that works, all we have to do to include that is just pound include hsv rgb.cginc. And now that will import all of the stuff from this file. Oh, that's .text. I got to rename that. If you downloaded this, it might still be a .text. Maybe I can just trick it. Do I have like Notepad? Yeah, Notepad++. Notepad++ is my hero. Sorry about this, guys. So that one's fixed. And that one's fixed. Okay. So now, get rid of those. And these are the text ones. So now, okay, we have syntax highlighting. We're good. So we want to do some rainbow stuff with our texture, but because our fragment shader is running on a per pixel basis, it's not as easy as just saying, I want rainbow to go from red on the left to pink on the right. All you really can do is just give one color for your pixel. So a good way to think about it is you're taking your pixel and you're asking what color goes there. So for now, we'll start by making our rainbow function do HSV to RGB. Our hue is going to be our UV's x coordinate, because on the left it will be 0 and on the right it will be 1. And then our S and V are going to be both 1 to make sure that we get a fully saturated color. And because we need an alpha, we're going to make it a float 4, and we'll make our alpha 1. So this will get us rainbow, hopefully, in the right direction for our texture. And there we go. You might notice that this is backwards. It's because quads are actually textured backwards. I don't know why, but that's what you got to do. I think they also might flip on the Z. Let me check the finished project real quick. Yeah, we have to flip them on the Z too. So yeah, I'm not 100% sure why. Unity is a little quirky sometimes. I'll save this. So we've got our rainbow. This is cool. But what we really want to do is make a circular rainbow, right? Because that's so much cooler. So this is where we have to start using a lot of math. And a good way to think about it is you need to take your inputs and slowly transform them to different forms along the way. If you've used Unreal, Unreal has a node-based material editor, and along the way it will show you what your material looks like after each step. And it's sort of good to think like that. So right now you can sort of imagine that if we didn't do any rainbow at all and we just said, I'm going to use my UV as input for the red and green channels, and then the blue is going to be 0, then our shader would look like this. So this is sort of how you can think of your input, where you have black in the lower left, and you have yellow in the upper right. You have red down here and green up there. So this is full X, this is full Y, and this is full both. That's 0 on both. So what we want to do is take this and we want to transform it into sort of like a circular pattern. So let's try to make it so we get that circular pattern. A good way to do this is, well, our circular pattern is going to be like a radius out from the center. So let's just take the length of our UV. You can sort of imagine that in your infinite grid, on your Cartesian coordinate grid, if you take the length of your UV, that'll be the distance away from the origin. So let's say that radius equals length I.UV. And instead of doing float4 like that, let's just make it so that the red, green, and blue are all dependent on our radius. So this will give us black to white, black if we're at the origin, and white if we're at least 1, 1 away. So now we're getting there. That's closer to what we want. We've got this sort of radial gradient from the lower left out. What we want to do is we want that center to be in the center of our quad, though. So normally what we do is we say, oh, well, I want that to move up a little bit. I'll just add, 0.5, 0.5 to it. This is actually not what we want, though, because this will make our whole thing white. And then suddenly, what's going on? I didn't expect for that to happen. And the reason why is if you think of it as like what's actually happening, when we're at 0, 0, we're adding a half to each of our coordinates. And now it's sort of like our input for the bottom left is the same as the input for our center before. What we really want is we want the input for our center to be like the input for our bottom left. And for that, we need to subtract a half on each axis to move the center down to here, or to keep the center fixed and move the lower left up to the center. So if we change this to minus instead, we'll get the result that we want, which is that we have this radial gradient with black in the center that expands out and gets whiter at the edges. If we want this to go for a full scale, black in the center to white at the corners, we know that the corners are 1/2 of the square root of 2 away from the center because we're 0.5, 0.5 away. So it's going to be 0.5 squared plus 0.5 squared square root. So what we can do is we can take this and what we want to do is multiply it by the square root of 2 over 2. Oops, wrong way. Do I want to divide the square root of 2 over 2? Maybe I mixed it up. Shader math can be a little confusing. No? Divide by square root of 2? Multiply by square root of 2? Okay. Pretty sure that's what we want. Sometimes with shaders, you have to play around with it a little bit. Use your eyeballs. So that's what we want. We have our gradient going out like this. And now we want that to be rainbow. And all we really need to do is just take that input texture that we have right now and apply HSV to RGB on it. And that will just map black to red. And then as we get closer to white, it'll go through the whole rainbow. So now we can just, instead of putting radius in these 3 spots, we can just do HSV to RGB of our radius. And it's yelling at me. Parameter 1. Oh, we need to pass in 1, 1. Okay, so now we have our rainbow. And this is cool. That's awesome. We're almost there. All we need to do is animate it now. So what we need is some time step to modify our input on. And luckily, Unity makes that really easy for us. It has a built-in _time. And this is a vector 4. You have x, y, z, and w. And basically, x is really, really slow, and w is really, really fast. So if you use x, things will happen real slow. And if you use w, things will happen real fast, and then everything in between is different speeds. So now the question is kind of how do we use this to make our rainbow scroll? And it's a pretty decent question. So we'll turn off the rainbow for now, and we'll just go back to returning our radius and 1. So What we want to happen is we want this to sort of like shrink in over time, and then after we go past white, we want it to start as black again and then shrink in. So one way we can do this is let's zoom out on our grid a little bit. So if we multiply by like 3, this will give us 3 times the rings. But really we can sort of see after we get to white, we just keep going white forever. And we want it to repeat. We want it to go black to gray to white to black to gray to white over and over. We want it to repeat. So what we can do is we can say this is going to be equal to this modulus 1. So this will say once we get past 1, repeat again starting at 0. And so now we have our concentric rings that we can map to rainbow. And if we turn our rainbow back on, we'll see now we have a lot of concentric rings of rainbow. Whereas before, when we did not mod by 1, oh, I think it maps that automatically. Ignore what I did for the thing in here. I'm pretty sure I just have some extra logic to do it automatically. But that's what we want. Now we just need to make it zoom in over time. And one way to do this is just add time.x. And now when we hit play, time will start going up. And you can see the rainbow is slowly going inward. So that's super cool. The next thing that we want to do is make this go slower or faster. So we're going to go up to our property section, and we're going to make a property that we can use to make it go slower or faster. So our property is going to be speed. We're going to call it speed. It'll be a float. It'll start at 1. This property is up here. So now we need to make sure that there's a matching one in our CG program. Like that. Float speed. And now we just want to take our time and multiply that by our speed. So now our time will progress at whatever our time is multiplied by whatever speed we give it. So now when we play, it will go at the same speed, but we have a little speed on our rainbow material. And we can pump this up, and it will go faster, up to really fast, up to really, really fast. And if we make this negative, it will go the opposite direction. So this is the sort of thing that we want. This is the rainbow texture. Super cool. So that's how to make a rainbow texture. That's part 1. The next thing that we want to do is do some image compositing, which is also super cool and fun. So we're going to make a new shader, the same way that we made the first one. Unlit shader. Image composite is what we'll call it. And we'll take our plane, duplicate it with Control D, and then move it over here. For some reason, when you move stuff, Unity steps the time step. So like, as long as you're moving it, it will continue to do the weird rainbow zooming, which I think is cool. Then we want to make a new material, and we'll call it image composite. We'll change our shader to unlit image composite, and then we'll throw that on our second quad. We will need 2 images from the repo. These are just ones that I picked out because they were on the Wikipedia article, but they will help us demonstrate our blend modes. We have an image composite source and an image composite destination. So let's go ahead and download these. We'll make a new folder for textures, and we'll have image composite source and image composite destination. So let's open up that shader that we made. We're going to start off by doing the same thing that we did originally, and we're going to get rid of the fog and the original property for the main texture and simplify it down to its very basic return color. But now what we want to do is we want to have images that we can put in, and we want to use some image compositing on them. So let's go ahead and make some image inputs, some texture inputs. So we'll have a source, which will be named source, and it will be a 2D. This basically says if there's nothing there, just return white. And destination, which will be called destination, and also be a texture, which will be white by default. So let's go ahead and make some sampler 2Ds for those. Visual Studio is not very good at editing this, but so we've got our source and destination, and now we can say float4 col equals text 2D. 2D. Let me check the other one. I should have the original shader for this, but I'm pretty sure it's text 2D of our source and i.uv. And then we'll return that. So this will sample the texture at our UV coordinate, which will get the pixel of the color in the texture at the same pixel that we're at on our quad. And it will give us that, and we'll just return that. So if everything goes as planned, we should just end up with whatever source texture we put in there as the image that appears on the quad. So let's go ahead and put a texture in there. So we'll put our source, and as soon as we put it in, we can see that this image that we put in source ends up right on our quad. This is super cool, but it's not quite everything that we wanted to do yet. We want to do some image compositing with a destination image. So let's go ahead and add a little bit of that. So we'll name this source and this dest. And we'll use, we'll sample the source texture into source and the destination texture into dest. And then we want to do some mixing and return whatever we mix them. So let's go ahead and include our CG Ink for the image compositing, which will be blendmodes.cgink. And we'll check that out to see what sort of things we have available. So this pre-multiply alpha and blend normal. Blend normal is basically the image compositing that you're used to when you've got two layers on top of one on top of the other in Photoshop or another image editor. And that will basically make it so if the top layer is fully opaque, it'll hide the bottom layer, and wherever it's transparent, it will let the bottom layer show through. Then we also have multiply, screen, overlay, hard light, and then divide, addition, subtract, difference, darken, lighten, all the basic ones that you would get in Photoshop. So let's use some of those to blend our two images together. So each pixel, we're going to take one from source and one from our destination, and we're going to return our blend. Let's not do normal because that'll hide it. Let's do blend multiply of source and dest. So now we'll set our destination texture to destination, and you can sort of see that our image has changed pretty considerably, and now we end up with, in the upper left, where the two images are exactly the same, we get really dark darks and like darker whites than usual, because our multiply has taken all of our values and sort of squared them. In the lower left, you can sort of see it a little easier, where we have a gradient of black in the upper left to white in the lower right, that we've sort of taken our image and we've just darkened it where it's dark and lightened it where it's light by multiplying those two values together. Our gray block just sort of took it all down one value, and then where it was gray on a gradient, you can see the gradient and it's darker than usual. So we've got all these cool blend modes. We want to try them all out. We can make a pretty simple, just an integer in here of blend mode. And we'll make that an int. It has to be int. We'll start that at 0. And then in here, same thing. We'll do int blend mode. And then all we have to do is say flip for color and switch our blend mode. So if it's 1, we'll go ahead and say our color is going to be blend multiply, source and dest. 2, I have to keep it open so I know all of our different ways that we can blend it. We'll screen them together. 3, we'll do blend overlay. And then I think it's hard light after that. Yep, hard light. We'll do blend addition. Blend addition is probably going to be the one that you use most often. It's a really simple, really easy way of taking two images and compositing them together. And especially if you want to overlay effects one on top of another, blend addition is usually the one that you want. Then we'll do subtract. Then difference, darken, and lighten. And by default, we'll just use blend normal. Okay. Big mouthful, but now that we have this giant switch written out, we can change our integer, that's our blend mode, and it will use a different blending function to mix our two images together. So switching back, we'll see it looks normal. That's because it's using the normal blend mode, and it's using the source image, which is like the top layer, exclusively over the bottom layer, because the top layer is fully opaque. But if we change this to 1, we'll get multiply. To 2, we'll get our screen. And then as we keep going, we can see some of the other image effects that we can get. This one is difference. Everyone knows difference. And once we get back to 10, it'll go back to using normal again. Yeah. So really simple, super easy. But in case you ever need to use them, those are totally free for you to use. Those image blending functions we'll be using a lot when we make our boost pad, because we basically want to take our rainbow and we want to use some images that we're going to lay over it, and we're going to blend those together using some sort of like mental Photoshop to get our boost pad. So this is all working the way that we want. Cool. We've got rainbow with time. We've got images we can composite. Let's put it all together. One more plane. Move that over here. One more shader. We'll make another unlit one. And one more material. So let's start putting all of these together. We're going to get some more textures for a boost pad. There are 2 that are on the repo as well. There's a boost pad, a detail. There's also a detail alt, which you can use if you don't like the detail. So let's go ahead and download our boost pad into our textures, and then our detail. And if you'd like to try the detail alt, you are more than welcome to use the detail alt. So basically what we want these to end up looking like is, they're easier to see now. Our boost pad will be some arrows that scroll up over our boost pad. Our detail will be some stars that sort of like lag behind them a little bit. And then behind all of that, we want our rainbow to be scrolling up our boost pad. So let's start with just some rainbow. And we'll open up our shader. Boost pad. Go ahead and do the usual, get rid of fog and main text. And because we need rainbow, we'll include our HSV RGB.cginc. And we want this to be rainbow from bottom to top. So let's go ahead and use just our y coordinate of our UV, because that will go from 0 at the bottom to 1 at the top. And we'll return float4 HSV to RGB of I.uv.y for our hue, then 1 and 1, and 1 for our alpha. So now we've got our rainbow from bottom to top. We want this to animate, so all we have to do for this is make our y coordinate scroll over time. So let's pull this out to, let's call it y coord. We'll start with our UV's y coordinate, but then we'll add our time so that it'll scroll up over time. We might as well make a speed, so let's go up here and make rainbow speed. And then we'll make it in our shader. So we'll take time times rainbow speed. And then we want this to loop every 1 unit. So we'll say mod 1. And now instead of using that there, we'll use y coord. So now we've got some stuff. If we move it back and forth, you can sort of see it scrolls. It's going the wrong direction though. So let's go ahead and take a look at our, we want our material for our boost pad. And let's switch our rainbow speed to negative. And now when we move it, yay, it scrolls the right way. So now we've got it scrolling the way that we want. Let's go ahead and hit play, and then we'll speed that up a little bit. Maybe like -10. That looks pretty good. Notably, anything you modify on materials while you're in play mode will stick, as opposed to any components that you modify while you're in play mode. Those will go away when you stop playing. So just keep that in mind. So the next thing that we want to do is we want to composite our boost pad arrows on top of it. So let's go ahead and make a spot where we can put our boost pad arrows in. So boost pad texture, default it to white, and we'll make a spot for that. And now, along with our y coordinate, let's pull this calculation out and say flip for rainbow. Is that? So that will be our sort of like imaginary background layer, is going to be our rainbow color. And then our boost pad color is going to be text2d of our boost pad texture at our UV coordinates, but we need to do the same sort of thing as we did with our rainbow speed. So let's go ahead and pull that out into a separate function. We'll call it scroll. We'll take in a float, and we'll output a scrolled float by some speed. And we just want to return x plus time.x times speed mod 1. So instead of having this ugly thing in here, we can just say that our y-coordinate for a rainbow is going to be scroll of IUVY by rainbow speed. And now we can apply it to our boost pad as well. We want our coordinates to be our same x, but our y, we're going to scroll. Right, need one more. So let's go ahead and make our boost pad speed. Same way we had it up here. We just copy and paste. We'll start at 1, same as the other one. And down here, boost pad speed. So we have our scrolling rainbow color and we have our scrolling boost pad, and now we want to composite them together. So all we have to do is return, we need to include our image compositing. I think that's the right name. Blend modes. And all we have to do is return some blending function. We're going to use blend addition of boost pad on top of our rainbow. So let's see if we got it right. This sort of makes sense what we're seeing because our boost pad is all white right now. So let's go ahead and change this to our boost pad texture. And now we've got a boost pad texture on top of our rainbow. And if we hit the play button, our boost pad scrolls down and our rainbow scrolls up. We have some nastiness in there though. I think that might just be some floating point stuff going on. So let's go ahead and make this go the right way. We'll say this is -5. And now our boost pad is scrolling in the correct direction. So we've got our rainbow and our boost pad. Now we just need to add our detail. And our detail is just going to be a repeat of the other two. We're going to make a detail texture and a detail speed. And copy and paste those. And then same thing that we did for boost pad, we'll do for our detail. UVX, scroll our UVY by our detail speed. And now we just need to add that blending to our current blending. So we'll just add another blend addition of our detail on top of both of those. And when we go back and set our detail, we can make these go up. Oop, -2. And we've got a boost pad. So that's all that you have to do to make a pretty good looking boost pad. This sort of effect will win you game jams. So that's the big takeaway. If you can write some good looking shaders, you can win game jams like nobody's business, because you'll win graphics hands down, because all you had to do was write a silly rainbow function and then composite some stars and arrows on top of it. This works in 2D as well as 3D, so feel completely free to use it in your 2D games as well as your 3D games. All stuff that you can use to make your game look really, really good. So that's how to make some basic compositing and generation with shaders. We've got a pretty good hunk of time left, so if there are any questions, I'll answer questions, and if there are any requests to try to freestyle some shaders, we can go ahead and do some cool stuff. Any questions? No questions. It's because shaders are so easy, I know. Does anyone want to do anything in particular with shaders? Dylan? Yeah, so you know what? I'm just gonna co-opt your question, and we're gonna do a cool shader. We're gonna get a Stanford bunny, low poly FBX. There's got to be one. Thingiverse, no thanks. I hope I don't have to do this, but we'll see. So for those of you unfamiliar, the Stanford bunny is like the bunny model that you've ever seen. If you've ever seen another bunny model, it's the Stanford bunny. You just don't know it. So let's go ahead and Stanford bunny obj. And hopefully I can get Maya to import this and make an FBX for me. I don't know if Unity supports OBJs. Maybe it does. We could try it. Okay, I mean, we can try it. Let's do it. Let's make a new folder for some models. And let's go to our desktop and move that in there. Okay, so yeah, so we got it. Don't even need to open Maya. And if you can avoid opening Maya, do it. So, that's our bunny model. Not super good looking. It's got some holes in it. Well, some wacky normals. So let's not import our normals. And it still looks bad. Kinda should have expected that. Smoothing angle 0, make it look like polygons. It's decent. Okay, well, we could fiddle around with meshes all day, or we could not. So let's not. Let's go ahead and pop this bunny in our scene. So that's our bunny right now. It is a masterpiece, but we could make it so much more cool looking with just a little bit of shading. So let's go ahead and make a new shader. Too close. Still too close. So all we have to do is go into shaders, and we'll make a new unlit shader, and we'll call this, I don't know, bunny. Feel bad naming it bunny because you can put it on anything. What we're gonna do now is use a shading technique to texture 3D objects using 3D textures that are generated. So a good way to think about it is instead of taking a picture and sort of like cutting and pasting and stretching and pulling that over the skin of our model, what we're gonna do is we're gonna take a big hunk of some material like marble or like zebra stripes or something like that, and we're gonna carve our bunny out of it so that our bunny has the same zebra stripes going through it as our original block, or the same marble going through it as the original block. So the takeaway is that it's going to be continuous over the surface of the bunny, and it's going to be continuous throughout all of space. So no matter what model we have, we can just throw the model in there, and our shader will sort of virtually carve it out of that 3D texture and display it for us. Sounds really complicated. It's actually not that hard. So let's go ahead and start with some simple zebra stripes that go through it. So we'll close our boost pad shader. Oh, I should probably make the material for it first. Can't get ahead of yourself. We'll make a new material, and we'll call it bunny. Unlit bunny, and throw that on there. So our bunny has no lighting at all right now. And that's fine. We can get away with that most of the time. But let's do something interesting with its colors. So let's go to our shaders and open up our bunny shader. Do our usual getting rid of fog and main texture. And now, instead of using our UV coordinates to determine how we want to texture our bunny, we're going to use its world space coordinates, which are going to be from the vertex property of our input. So let's go ahead and just say that that we're going to return a float 4 of i.vertex, comma 1. And we'll see what that gets us. And our bunny looks pink because something's wrong. Ah, right. We only want XYZ. Okay, so our bunny looks super yellow right now. Show me the bunny. And that's probably because we have it way out where X and Y are 1. Not sure why it's not bluer, but let's do zebra stripes with it based on Y coordinate. So it'll look like black, white, black, white, black, white. So let's get our Y coordinate. That's going to start off as vertex.y. Oh, is this going to be screen space? It might be screen space. I could be fooling myself. Yeah, no, that's why it's yellow. Let's do that. Vertex SV position. Let's see if that gives me a rainbow cube bunny. Oops. I think my bunny is suddenly in a very bad position. Oh, I probably need an extra parameter. Here we go. This is the exciting part where you have to actually fiddle with your shaders a lot. World, we'll say that's going to be position. See if we can get away with that. .44. Okay, so let's try. Yeah. I can. It'll make no difference because it's still using float, but yeah, I can do that. I think I might be able to use a text coord. Let's go check the Unity documentation. This is where you'll spend most of your time doing shaders. Okay, so they pass it through text coord 0. So we'll steal this one. And we'll use text coord 1. We don't actually need the UV coordinate. Ooh, that one needs to be left alone. The other one we can change. Let's get rid of that. And instead of this, we'll use that. And now instead of using vertex world, I'll use UV. Please work. Sure. What's it saying? Input. Okay, so I see darkness. We're slowly getting there. Okay, we're gonna steal this guy's code. Shaders are not an exact science most of the time. How's everyone doing today? Pretty good? Having lots of fun? Game Dev Club? You don't need Ray. And our fragment shader is going to be V depth. Oh, you know what it could be? That. Should be pause, and that should be pause. Okay, let's see if that did anything. Yeah, so now we got crazy stuff going on. So see how that's absolutely insane? You can't tell anything that's happening? That's good. So let's make this bigger, like a lot bigger. Let's try making this like, let's actually make this a parameter we can tweak. Scale is gonna be scale, float, start at 1. We're gonna mod by 2 times our scale and make our scale up here. And then if our y coord is less than our scale, we'll use black, otherwise we'll use white. Okay. And now let's go to our material and start tweaking that value. Make it bigger. Yeah, now we've got a striped bunny. So, oh, we're in screen space right now. That's no bueno. We're like in pseudo world space. Oh well, I still think it looks pretty trippy. So, one of the many cool things you can do to make it easier to texture your models and stuff. If you don't have time to skin models, writing shaders is a great way to make it look like you had time to skin your models. I'd love if we could get rid of that weird distortion stuff. Let's try that and see if I was actually wrong. No, that just puts it in screen space, which is also cool, but let's try passing that through a text coordinate. Oops, wrong struct. So let's pass that through. And world pause is going to be that. By our v vertex. So let's try using world pause.y. And errors. Object to world. Thought that was right. Maybe it's not. Oh my gosh, it turned black again. Let's turn our scale down. Okay, we turned white. Is there a sweet spot of not being bad looking? Oh, I saw stripes. Okay, I saw stripes, then they immediately disappeared. Okay, so the good news is that we can get stripes. If we make this one that's too big, 0.0321, 0.001, 2. Okay, well apparently this has to be real small. So let's just multiply it by 100 in our shader. Oops, divide by 100. Now if we put in 2.2. No, not having it. Need this one. Yeah. So now we can make our stripes bigger and smaller until they get too small and then they disappear. So we're going to use this same concept to give us an additional layer of stripes and turn it checkerboard. And our checkerboard is going to be real cool, and then we're going to build off of that to make something even cooler. So we'll do the same thing. We'll make it the real scale. So our y-coordinate is going to be, we'll make this an integer now, and we'll say that it's our world pause mod our real scale. Oh, actually we can just do floor world pause times real scale. And then our x-coordinate is going to be the same thing. Move those around. And then we'll say if x-coord plus y-coord mod 2 equals 0, then we'll use black, otherwise we'll use white, so it'll alternate. And let's try changing our scale again. Is that doing anything for me? Looks like it's not. Do I need to get rid of this 100 now? Is that how we're going to do it? Yeah, now we're seeing it. Let's make this 1050. Okay, so now we've got some checkerboards on our bunny. So this is where it's easier to see that sort of concept that I mentioned, where if you had sort of like a checkerboard block and you carved your bunny out of it. So now we've got checkerboards that go around sort of like this giant sphere, except it doesn't look quite right. Let's see if I missed something. X plus y mod 2. Looks fine to me. Let's try normalizing our world pause. No change. Awesome. Oh no, duh. It's because that's along the z-axis. Sorry. So, if we add one for our z-axis, z-coord, world pause z times scale, and then we just add that into our calculation over here. Then we've got a real 3D checkerboard bunny. So now that we have this checkerboard idea, let's do something cool. Let's make these little spheres inside of each checkerboard and texture the bunny with those. For this, all we have to do is take our 3 coordinates, and we need to sort of translate our coordinates overall into those tiny little cubes. So all we have to do for this is say float 3 chords, or just use position, equals float 3. I think we can actually do world pause minus floor world pause times scale. And that'll do it for all 3 of them at the same time. And then we'll just do, our color is going to be pause, comma, 1. That should give us repeating color cubes inside of our bunny. Cool. We've got some color going on. Did I forget scale? No. There we go. So now we've got these repeating color cubes inside of our bunny. So we're going to use these color cubes as this imaginary little unit cube that we're going to work inside of. So instead of returning a float depending on the position inside of it, we're going to go ahead and say that we're going to use our trick of moving the origin to the center of the cube, and then we're going to do a radius around it. So we're going to say pause minus float 3, 0.5, 0.5, 0.5, and we'll get the length of this. So this will say, what's the radius? You can just pull this out. And if our radius is less than, let's say, 0.7, we'll just return black. Black will be 0, 0, 0, 1. Otherwise, we'll just return white. So now, I think that might have been backwards, because our bunny is looking sad. Oh, if it's greater than. Let's make that 0.5. Yeah, so now we got dots on our bunny. So those dots are like carving our bunny out of a material, which is a bunch of spheres that are checkerboarded across the whole thing, just stacked on top of each other and then layered like that. So now let's turn those spheres different colors, because that is the raddest thing to do. So we'll go ahead and get our world position integer coordinates, and then we'll use those to rainbow color each of our different ones. Steal that out of there. And then we still want our black around the outside, but now we want to use these integer coordinates. So let's return a float that is going to be int coords x. We actually want, first we have to include our rainbow. HSV RGB. And then we want to do HSV to RGB on the sum of our coordinates. But let's go ahead and take those and divide them by maybe like 6 or something. We have to at least divide them by 3. Otherwise, we'll always end up at 0. Let's actually do like 18 or 20 or something. 1, 1. See what that gets us. Shader compilation errors is what it gets us. Oh, because we need those gone. Okay, so now I've got a rainbow bunny going on. which is pretty cool. Our rainbow bunny is pretty rad, and we can put any model in here, and it'll texture it the same way. Let's turn our scale down a little bit so that we can see it a little bit better. By that, I mean turn our scale up a little bit, so it'll get finer. And now our bunny looks pretty disco. And we did all of that without having to texture our model at all, which is the big draw of shaders. So if you're on a short time restraint and you can't afford to spend the time doing this, you can't afford to spend the time texturing your models, shaders are a great way to cheat because they're usually not that hard to write. And if you have some ones that you have canned, you can usually modify them on the fly to get some pretty good looking ones. Any questions? You can animate this too, and then it'll look really rad. So let's go ahead and animate it for fun. We'll go ahead and say that our position is going to be that, but we'll go ahead and add some time. Float 3 time x 0, 0. Ooh, I think I might just need to add this raw. Okay, so now our bunny should move over time. So let's see if it does. Yeah! And now our bunny looks like it's from the future. So, that is that. Anything else anyone wants to do? Did I at least sufficiently entertain you, Dylan? Any other questions about stuff related to shaders? Anyone excited to go try shaders now? Okay. Well, I hope that this was at least informative for you. Thank you all for coming, and have fun with shaders in the future. That's that. The end.